Certainly. Thanks, Dan. This will not be down at the level of silicone and talking about what's on there. We will mention and spell TPM for you. But this is really a huge subject. I mean, it could be a 4-year degree when you get into the cryptography, when you get into the safety aspects. It really is a whole lot. But in an hour, we're gonna talk about some concepts and sort of give you a flavor of how this affects what we do every day a lot around here. I want you to think about the project you're working on or the last project you worked on, and I want you to think about the worst thing that could have happened or could happen. Does a system crash while 1,000 users are on it? Do you lose money for a client? Do you become the source of the latest denial of service bug because of your code? All of that and the stuff that we deal with most of the day, most of the time is really sort of pales in comparison when you look at IoT. 2 years ago, these guys in California, college students, hacked a Jeep. Without touching the Jeep, over the internet, they could control the steering, the brakes, the accelerator. I'm glad I didn't write that code. They were good guys, so that was a good thing. Heart implants, defibrillators, pacemakers can be hacked. They denied it for a while, but the FDA went in and figured out that yes, there's a flaw. They fixed it, but not a good one to be involved with there. Yeah, I mean, you can defibrillate somebody remotely and just, you know.
Part of the strategy might be, let's attack the battery. If they just make Wi-Fi work a lot or something like that.
Yep, drain the battery.
Drain the battery.
Definitely an attack that can be done with that. How many people have heard of Stuxnet? The first weaponized virus. There were actually 2 of them. They worked in different ways, and they were delivered by different methods, but they both attacked cascades of uranium enrichment centrifuges in Iran. These are industrial control devices that are air-gapped from the world, and they still got a virus in there. We don't know who it was. So, but it basically started breaking their centrifuges. Last fall, if you had trouble getting on the internet, somebody wrote a virus that used the standard user IDs and passwords on DVRs and cameras and got them to create a distributed denial of service attack. Couldn't get to Netflix, couldn't get to CNN, all these places.
It brought us down too.
Yep. So they say the largest one in history. This one very recently. Ethereum is a blockchain cryptocurrency, a lot like Bitcoin, but it does a lot more other things. A coding error led to $30 million being stolen in Ether, which is the Bitcoin of Ethereum. And that was a week after $7 million was stolen. And it's not a problem in the encryption or in the blockchain technology. It was a problem in the wallet. And this one was because of one word that they left out: internal. So scope does matter. Hopefully we will never see any of those. But security does matter. And I think a lot of times we can be very slack and very casual about what we do because we're not involved in those sort of things, and we're in more mundane business apps, in the server room, limited user base, and those sort of things. But as we get into the IoT, a lot of that changes. So we're going to talk about what is this Internet of Things, make sure that we sort of have a common definition if there is one. What's the deal with IoT projects? How is this going to be different when we start doing with Internet of Things and pulling that into our projects? What are some security fundamentals that we ought to know about regardless of what sort of system this is? What are some things that we may not have really had to think about or deal with before? When we get into those projects, how do we assess IoT security? What are we looking for, and how do we measure and grade ourselves against some security metric? And then how do we build IoT security when we're working in these projects? So what is the Internet of Things? It seems to be this sort of catch-all that is getting all of these different names that different groups have given it. They're trying to describe how these enabling technologies are making their way into their specific worldview, whether it's an industry, whether it's a factory, whether it's a smart home, a smart city, a smart grid, all of these things, people are trying to make it their own. And this sort of gives you the idea of the breadth of the IoT, but it also sounds a lot like marketing hype. You know, let's put a little name, put a little TM beside it, and you know, this is the latest, greatest thing. So maybe a definition would help. The Internet of Things is an integrated part of future internet and could be defined as a dynamic global network infrastructure with self-configuring capabilities based on standard and interoperable communication protocols where physical and virtual things have identities, physical. Okay, this is the most verbose definition I've ever seen. And it is actually by a group called the Cluster of European Research Projects on the Internet of Things, or SERP IoT. You can just call it cluster. Maybe a simpler definition. Sensors connected to the internet, making connections, sharing data. This is Kevin Ashton, who in 1999 was working for for Procter & Gamble doing RFID projects, and he coined the term Internet of Things. So that may be as close to the intent at least, but it's still not very satisfying. What does internet-like way mean? Sharing data freely. We're in business. Why do we want to share this stuff freely? Unexpected applications. Humanity's nervous system. This sounds a little pie in the sky. So maybe if we look at problem domains. So we knew all those names, industry and grid and smart home and factory and all these things. There are a handful of domains that this is really becoming popular in, and if you do searches, these are the things that come up. These sort of areas where IoT is being applied. So if you look at industrial, well, we can break that down. Digital engineering, that has to do with document management, prototyping, simulation, product manufacturing, robotics, machine-to-machine links that have always been there. Monitoring and maintenance, sensors, movement, vibration, predictive analytics. All these different things get wrapped up in there. So that's a whole lot to digest in one problem domain of industrial. So what about automotive? Well, infotainment, you've got GPS, mapping. You've got eCall, which is the Europeans' answer to OnStar. It's going to be mandatory next year in all European Union cars, so they will alert if there is a crash or an airbag deployment. Automated driving, the holy grail, everybody's sort of waiting that they can just sit and read a book on their way to work or take a nap. So what about power? Maybe that's simpler. Well, that's the entire power grid and distribution. And if you look at storage and marketing and sales, when you get into microgrids and people feeding power back into the grid and getting paid for that or offsetting cost with that, this gets even more confusing. Plus there are connections all in here that these silos sort of start breaking down, where consumer goods with new capabilities come out of manufacturing and go through sales and marketing, and smart grids start being interfaced with power generation and transmission for load balancing and power predictions. So why all the confusion? That's a whole lot of stuff that's, as you say, IoT, 3 letters, and you get all of that mess. So everybody sees what they want to see. IoT sounds like a technical term, but it's really blind men and an elephant. Everybody's got their own little view on it, and it may be a tree trunk or a rope or a snake or whatever you think. But everybody sees what they want to see. And everybody makes it their own. It's my industrial IoT, it's Industry 4.0, it's a smart grid, or a smart anything. It's doing things better, faster, and cheaper that you've always done, whether it's in a factory or a consumer good or a power grid, and it's creating new opportunities and creating new markets. So maybe it is everything to everybody. Maybe it's what you want to make of it. And regardless of this, it's something that we've got to deal with, as we deal with customers who are dealing with this and they're coming to us with questions. So instead of saying why all the confusion, maybe we just say why all the interest. That's a graph of connected devices worldwide. We're down here. 2020, this source said 30 billion connected devices. ABI Research says over 40 billion. Gartner says over 50 billion, all by 2020. So the slope of that curve may be in question, but up and to the right is not. Also, the size of the global IT market in dollars. There's this almost universal appropriation of IoT that's driving these, and if these are halfway correct, then this is going to be our reality for the next however many years until Industry 5.0, until the next big thing. This may be the force in IT for many years to come. So how did this happen? All these technologies have sort of reached a tipping point where all these things that used to be very hard and complex are now possible in a cost-effective manner. Things like Moore's Law, increasing performance and decreasing cost. I love this graph. Gordon Moore in 1965 said that basically computing power will double every year. And he expected that to last for at least 10 years, 1965. This is 40 years later, and this is using just Intel chips. And this is a logarithmic scale. And that's out through 2005. Some people say it's slowing down. It probably is. But this is a force that nobody could have predicted even in 1965 when he said, well, maybe 10 years this will go on. Wireless connectivity, Zigbee radios, Bluetooth LE, 4G, 5G. There are ways to make these assets always connected. So you don't have to worry about where something is or when you can get to it or how you can get to it. All of these things are available because of wireless technology. Battery technology means that assets are now mobile. They don't have to be plugged in. They don't have to stop in just one place. Sensors are becoming smaller, faster, cheaper. I saw part of one of the NASA auctions that stuff has come up. They had one of the IMUs, the inertial measurement units, off of one of the Apollo trips. And it's about that big. It's got some sort of lead or titanium base. And it's like a 6-axis IMU. You can now get that on a chip the size of a grain of rice. So these sensors that can do things that we never thought of before. Big data can ingest and analyze this data from these sensors like never before. I mean, it used to be if you had these things spitting out data, there would be nothing you could do with it. And the cloud has really given us a global, data-centric way to process these things. So with all those things and us having to deal with IoT, what makes IoT projects different? Two big reasons I would say. The first is clash of worlds. And these will look familiar, at least the left side, to anybody in this room. The internet camp, that's us. And the thing camp, that's the engineers, the electricians, the bolt jockeys. And there are a lot of differences as you go down through here. Some of them are sort of stereotypical, some of them may not exactly apply. But if you look at these, then you can sort of see that these really are sort of different worlds. You know, the internet camp works with, you know, typically high risk and VC-driven cultures. I always like the motto of venture capitalists that you should fail often, fail fast, and fail cheap. That doesn't work in the thing camp very well. We're typically working in agile methodologies, whether it's Scrum or Kanban or extreme programming. We're looking at fast deliverables, working software. The thing camp is typically waterfall methodology. They're very precise in their engineering, and the background that they come from is very precise in that way. We use a lot of open source software, very standard driven, whether it's ISO or more international standards like DIN. We're doing perpetual betas, that minimum viable product. They're looking at long lead times. So we've got sort of clash of cultures going on here. We've also are connecting cyber physical systems, and this is sort of a big buzzword in the IoT, especially when you get out to the edge and start talking about security. And sometimes it's worth stating the obvious. These are the things in IoT. This is sort of what makes it fundamentally different, is that there are things in the world that we're dealing with, and that changes a lot of how we look at the world. If we're manipulating something physical over the internet, you sort of open up a whole can of worms that we didn't have to deal with when there's a server locked in the server room, you know, serving out an application to the people in this office. So the Internet of Things and these cyber physical systems create a lot of security problems. Most engineers who come from the security and the hardware world, the thing camp, rarely had to address data security, not something they really had to think about. It's on this device, it's ready to go. Most software developers, even if we say that we're very security conscious and we build that into all of our systems, we haven't really had to address safety. My server's not going to do anything that I can really control from where I sit. And these projects can get in a tug of war, and all projects sort of have competing requirements. And I think in IoT projects, in a lot of ways, these are multiplied. So the first requirement is capabilities. The device should help the world. I want to do something useful. I want to do something that's good for business. And that has quick development cycles, virtual testing, frequent updates. All these things are going to help me drive these capabilities. Well, another requirement, I just cut something off, is safety. The device should not harm the world. This is what we were talking about a minute ago. So where to deliver capabilities, I want to move these things very fast. I want to use virtual testing. I want to get through a lot of iterations. Safety is going to put the brakes on that and say, hold on, we got to test this thing thoroughly. We've got to go through some outside certifications, all of these other things that are just going to drain my ability to deliver capabilities. I want to do frequent updates over the air. I want to put on-device capabilities. I can't handle all this stuff back at my server room, so I'm going to put a lot more processing power capabilities on the device. I'm going to go through multiple third-party providers. I don't want to reinvent the wheel. If somebody has a component I can use or a service I can use, I'm going to use that. And a lot of times I haven't really thought about how much I need to trust them or what their environment is like and the people who they're trusting. And this gets pulled by another requirement of security. The world should not harm the device. So when I'm trying to do over-the-air updates, I got to do that in a secure way. When I'm putting capabilities down on the device, I've got to be able to lock that down so that it can't be co-opted to do something I don't want it to do. When I'm talking to these third-party providers, how safe are they? What sort of security do they have in their world? I also want to do open data sharing. I want to future-proof my data collection. I've got all this data coming in. I'm not sure what it might be used for, where the value might be, what big data is going to show me in this huge data set. So I'm going to collect this and I'm going to share it and I'm going to use other people's data as well. Well, Now this is getting pulled against the requirement of privacy, that the device should keep the world's secrets secret. I can't just share everything. So if you look at those, what makes IoT security different than just the security that we should build into all of the products that we do make? There's a much larger attack surface. I'm putting all these devices out there, whether it's 30 billion or 40 billion or 50 billion. Even in one industrial implementation, if I've got thousands of devices, these are just all these places that I'd never really thought of before. There are more places to attack, and there's more value to attack. If I saw value in putting all these things out there, maybe one of my competitors or a hacker or somebody else may see that as well. So it's like putting a big neon sign that says, "Hack me." There are many more attack vectors. There are many more ways to get into these things. Industrial controllers aren't purpose-built anymore. They used to be discrete components on a circuit board, or they used to be sort of minimal logic to do what this needed to do to control this process. Now they're computers. They've got logic, they've got OSs, they've got all of these things on there that I'm using for all of this great capability, but somebody else can use it as well. How am I going to secure that? How am I going to lock that down? There are more third-party integrations and interactions. Again, how safe are these people? I've got to talk to this person. I've got to share keys with this person. I've got to let them into my processing space. How am I going to control that and make sure that that's safe and something that I can reliably deal with going forward? The cyber-physical systems have security and safety concerns. Again, this isn't just a server sitting there that crashes and loses money. You leave out that internal statement, and now these chemicals mix in a different way and blow up the plant. This car crashes into another car because you said turn right and took that to mean the other right. Big data really changes everything. The value, how it's collected, what it's used for, the volume, brings up all these different questions about security and about privacy that we've never really had to deal with. And it is, I'm not sure that it's really fully understood as people come and say, I want to get involved with this. We could do a whole thing on big data and security and big data. Just replace IoT with big data, and it's as big a subset of that as IoT is. Physical access and control. Again, we're not in the server room. I may have devices out there that are not under my control. If I'm doing fleet management, they could be driving all over town. The iPad that I've issued to my service technician is now on the Wi-Fi at Starbucks with who knows who else. So what happens when you lose physical control of these things? So let's talk a little bit about the fundamentals of information security. And this is not something that we can delve incredibly deep into, but I think it's good to get sort of an understanding of some of the concepts that we've probably all seen. We may understand a little bit. This may give you a good chance to think about them some more and some places to dive in a little more later when you see a need for this or you see something that piques your interest. There are typically 5 pillars of information security that people talk about when they talk about computer systems. Always like non-repudiation. I need that with my wife sometimes, I think. You did tell me that, so you cannot deny it. So these are typically with sort of standard information security. The Internet of Things adds a couple of others. The first is resilience. I'm typically mirroring something in the physical world. I need to keep track of that. I have to have state awareness. I have to be able to respond correctly to disturbances and in a way that coordinates the physical with the cyber. So if the computer has to shut down for a certain reason, can it bring the physical world to a state that's stable and maintain its state for the next time it comes back up. And also safety, as we said, the system should not harm the world. These don't exist in typical ways that we think of information security. So how do we do these as part of developing products for the world? The number one way and the number one thing that sort of envelops all of this is cryptographic services. The confidentiality, integrity, authentication, and repudiation can all be handled with cryptographic services, either encryption or digital signatures. That is what rules the world now of security. So let's talk about some of the concepts of it. Again, a lot of these I think everybody has sort of seen and used in different places. Symmetric encryption, I want to hide a document. So I've got a document, I apply a secret key through this algorithm, and I get something that nobody in the world can read. I send it over to somebody else, they've got the key, they run it through the algorithm, they've got a document that they can read now. And it's great. Anybody who gets this document has no idea what it is and probably has no way to do that, especially if you're using the AES encryption, at least 128-bit, although 256-bit is better. Now, the problem here is I've got to have the key and you got to have the key. How did I get you that key? Well, if I send it to you in an email, then anybody who wants it has got it. So there needs to be a little bit better way. So now we've got asymmetric encryption. So symmetric means we both have the same key. Asymmetric means we have different key. I've got a private key that I'm never going to tell anybody. And I use that to generate a public key and I send it to you. You take your message, you run it through the algorithm with that public key and you send it to me. Now once you encrypt that message, you can't even read it. So it has been encrypted. Nobody else in the world can read it except for me with my private key. So this is a little bit more secure because I don't have a public key that I've got to send out to the world that can decrypt that message. There's one algorithm that does this, it's RSA. Now the biggest limitation is it's only able to encrypt data to a maximum amount of the key size. So if you have a 15K key, that's the biggest piece of data that you can encrypt. So typically what this is used for is in the transport layer security is the handshake protocol. I've got a private key, you've got my public key. You're going to tell me that you want to make a call. I say, okay, send me that message. You send it to me encrypted. I decrypt it and say, okay, now we've got a channel. I'm going to send you a public key that's a session key, so it's not valid for long, but we're going to use that to do our encryption because then I can do big blocks of data. And it's much more secure encryption in the symmetric encryption algorithms and able to handle a lot more data a lot faster. So asymmetric encryption is very important, but it has its limitations. It's not as secure as symmetric just in the encryption algorithm, but it's more secure in that I don't have to share the same key to everybody. I'd seen something years ago that I think the 1K key, the 1024-bit key, would be sort of regularly hacked by brute force sometime around now. So they keep making the keys bigger and bigger, which needs more computational power to do this. So it is an algorithm that has very specific uses, but is a very key part of cryptography as it deals with security in computer systems. The other concept is the cryptographic hash. Most people have used this, the one-way hash, the SHA-1. Let me take a password, one-way hash it, store it in the database. Nobody knows what it is. All I can do is take another password, run the same algorithm, and compare to make sure that they match. It is a functional representation of any amount of data, and it puts it in a digest that's a fixed length. It is unique to that piece of data that you gave me, and it discloses no information about that data. So I can't look at a hash and decipher what you might have sent me. It's not a decryption kind of situation. So we've got symmetric encryption, we've got asymmetric encryption, we've got hash functions. If we put that all together, we can make a digital signature. And this is a little bit small and can get sort of complex unless you follow the arrows carefully. So if I have a big piece of data, I run it through that hash function, and it's going to make a unique fixed length digest of that piece of data. So that hash is unique to that piece of data, and it's a small and fixed length. So I can now run that through my asymmetric encryption because I can use my normally sized private key and make a digital signature of that, which is an encryption of a hash. I can take that and I can combine it with a certificate and my data, and I can send that out into the world to the people that may need that. Somebody on the verification side will get that, and they will take that and they'll split it back apart, and they'll take the data and the signature. They'll take the data and they'll run it through that same hash function that they did up here, again, just like you would a one-way hash in a database to store a password. And then you take the signature that was on there, which was that encrypted hash, you'd run it through the public key that I'd given you since we're now communicating, and you'd get the result of that decryption, and those hashes should match. That gives me integrity. I know that that data has not changed from when it left me and got to you. And it gives authentication. I know that the person who gave me that public key is the one who sent me this information, and it can be nobody else because their private key is completely secret, which is another issue. If this is using asymmetric encryption, then I've got the integrity and the authentication. Now, if I use symmetric encryption here, which means there's one public key and we're both using the same one, I've still got integrity. I still know that all the bytes that are here end up over here, but I don't have authentication because anybody could have gotten that key. I emailed you that key. So that provides what they call a message authentication code. So what are the risks to cryptography? This is what all of this security is based on. This is what the world runs on today. The failures of cryptography are due to the implementation and the integration, mainly because you do them wrong, or you misunderstand something about what you're doing, or you don't apply it correctly. Cryptography requires large, secure, good random numbers, and these are very hard to get. Computers are deterministic. You start an algorithm and it's going to run the algorithm the same way every single time. You run the RAND function or the RNG or whatever it is in any operating system, and there's some great visualizations of this. People will map these on squares or different sizes, and you will see immediate patterns in there. These are not random numbers. They're not even pseudo-random numbers. More and more implementations are picking up on some low bias sources of entropy, which is what really drives an RNG. So mouse movements, packets of data on a transport on a network card. So it's all the data at the same time. There's really nothing that can bias that. There's no way to affect that in a way that could be used as an exploit. CPU interrupts. These things come in from so many different sources that they really can provide pretty good sources of entropy. Yep. Just the random noise. Now, that can be not quite as low bias. You can affect that by certain things. There's some things that use temperature as well, and those things can be biased. A lot of people are also trying to combine some of these things, so you can get add more and more entropy to this random number generator, which is where you get your keys and where you get all of the basis of of cryptography. And if you don't have a good random number generator, if that's compromised somewhere, then the rest of the game is over. It doesn't matter what my private key is. If you can determine what random number I'm going to get next, then you've sort of broken the root of trust here. Poor key management. Your private key is always secret. Nobody ever knows your private key. Well, that can be sort of a hard thing to do. Even when you're sending out public keys, when you're doing session keys, key management really needs to be managed pretty well. And I didn't go into a lot into public key infrastructure, but that's sort of part of the domain that manages this, that guarantees that keys are well formed and from known sources. You've got certificate authorities that can vouch for keys and can be used in chains of trust. You also have to understand the cryptographic boundary. Where is this encrypted? Where is my key? If I get a nice encrypted message and I use my private key and I decrypt it and then I store the decrypted on my hard drive, I better hope that the cryptographic boundary is outside me, because if there's somebody inside who wants to see that message, they've got it. So where is the cryptography being applied here? That brings us to one of the best solutions for this, and one of the most ubiquitous, and one that will get as close to silicon as I think in this, and that is the Trusted Platform Module. It is a hardware security module. It is a chip mounted on a motherboard. There are other hardware security modules that are add-ons or pieces of hardware that sit in a physical computer or data center, but the TPM is typically mounted on the motherboard, and it has a lot of functions built into it and a lot of capabilities. At manufacture, it has an RSA key built into it, sort of a GUID, unique, never shared, should never leave the TPM way to root trust into certificates and keys. It has a high quality random number generator using some of those sources of entropy we talked about before, and that's built in there. It has engines to do hashing and encryption and decryption, so your keys never need to leave the TPM. Typically it has storage for these keys that as you collect public keys from other sources, you've got a key store on here. A lot of them have tamper protections that you can't physically interface with them without causing problems or causing them to malfunction. They provide secure boot. They have a digest of all the hardware and software and the configuration on your machine. So they really give you a good root level of trust. They're what provide disk encryption in Windows 10. If you say, I want to encrypt this disk, the TPM provides the key to do that and provides the algorithm and the processing to do that encryption. So how are we going to use this in IoT communications? We got a lot of different protocols, we got different algorithms and standards. And an IoT implementation, what does it mean to use cryptography, and how do we know that it's doing what we think it ought to do? Zigbee is one of the leading methods, one of the leading wireless communication for IoT. It's got a great distance, it's got a good throughput, it's RF based, very small modules that it's easy to integrate into a lot of different things. It uses the 802.15.4 MAC layer, which is the standard that it's based on, which supports AES algorithms with 128-bit encryption, which is the government standard. That's optional. There are a whole host of authentication and encryption options for a Zigbee radio. So again, if I set it up with no encryption and no authentication, it's just clear text getting sent over there. So you need to be careful about how you're setting these up and that you're using an appropriate level of security. Bluetooth LE is another communication standard protocol that's being used a lot in IoT. And it has a surprise. I didn't know a lot about Bluetooth LE, but it actually has a fairly sophisticated security mechanism and usage of keys within it for pairing and bonding, authentication and encryption. So it is a sort of a viable short distance connectivity protocol for the IoT. Near field communications, there is no encryption provided. There is no security. These are typically used just to bootstrap into another protocol to do some handshaking. What about messaging protocols? MQTT supports TLS, so you're using SSL for your communication. You've got application level client identifier credentials for the authentication, and those are wrapped up in the TLS, so I know that in flight they are secure. Other protocols, we've talked about a lot of them in here. CoAP, it supports a datagram TLS, which is sort of like regular TLS, but it's optimized to run on small devices very efficiently. XMPP, that uses a simple authentication and security layer, which is oftentimes used in conjunction with TLS. AMQP uses the same thing. So all these provide security, and they recognize that, but they need to be monitored, they need to be set up, and they need to be used correctly. So if you're talking about security in IoT, you've also got to talk about identity and access management. So now we can talk securely, but how do I know who you are? How do I know what that device is? Somebody pops up on my network. Do I provision him? How am I going to go about figuring out what he should have access to? So back in the day, administrators were concerned with people.
Back on the last slide where you had MQTT.
Yep.
You always hear about how MQTT isn't as secure like AMQP. Is that because of hacks to the brokers and not the transmission layer? But why is it that?
I don't know. It probably has to do with what the endpoints are doing. And I wonder if some people have some knee-jerk reactions when you say your credentials are in the message. What, you're putting username and password in the message? Well, it's going over TLS. So between me and you, and we're trusted parties, nobody can see that. So I'm not sure why it gets a bad rap, but it does sort of, I think, come up as, you better watch out. And there are people that are always trying to come up with something, whether it's AMQP or any of these other ones that could be better message brokers, that could be better protocols for that sort of thing. So, identities and access used to be about people. Then it was about personal computers and remote personal computers. I've got to set up a VPN, remote networking. Then it was bring your own device. I've got my phone I want on your network. I've got clients coming in, they want on my network. Then the IoT explodes and we've got however many devices you want to say are now going to be out there, and they're all going to be connected to this. And I've all got to identify them, and I've got to give them certain authorizations on my network. So this has got to scale from a point where it used to be about a few people and then about a few people and a few devices to an order of magnitude larger than anything that's supported today. It's got to deal with devices that we may not even know what they're going to be doing in the future. Again, these are not purpose-built, discrete electronics. These are computers. These are things that are going to be reprogrammed and doing different things in the future. What that is, I don't know when I deploy or provision these. If this data is flowing around, is it going to be shared outside of my organization? Is it going to be available anonymously on the internet? So when you're talking about identity and access management in IoT, one of the things I kept coming across is build on what you know. So if you look at this sort of building up the stack, you've got IPv4 or 6. You've got the security protocols, whether it's transport layer security or DTLS or SASL that some of those protocols are using. You've got the IoT protocols that use that we're building up. And then you've got, for different purposes, you've got different ways to identify people on that. You can use token-based authentication like OAuth. So this device has an identity that's unique. It can talk to me and validate itself and authorize itself with me. I can limit IP devices based on their IP address and their access to my network. I can provision keys through my public key infrastructure to devices that aren't smart enough to do those other things, but they can embed a key in them, like a wearable or a sensor or things like that. So I can do identity management. I can identify my relationships and use the different devices within this network. I can have device password management since I've given them a key, and I can integrate that to my existing identity and access management, and I can integrate also with my existing physical access control systems. So the RFID card that you use to get into the building, some of these devices that aren't as smart. So a lot of this is stuff that is already in use, that is already known to people who provision systems and build systems and secure systems. So let's talk a little bit about assessing IoT security. So we've got the Internet of Things we know about. We figured out some things we're going to have to deal with about projects. We know a little bit about cryptography, about identity and access management. Now we're going into a project and we're going to figure out what this is going to look like. So when security engineers are assessing a system, they're typically looking sort of in three big areas: threats, vulnerabilities, and risks. And threats are really the exploit potential. It's not the source or the actor. It's not the guy coming to rob you. It's the act of being robbed. They could be natural or man-made. You're now sort of outside the server room and you're exposed to a lot more threats than the typical things that you might have thought about. Vulnerabilities are weaknesses in the system. They're the target of the exploit. What am I going to pick at that I think that I can get into this system and I can cause some havoc? And risk, that's my exposure to loss. That's the result of the exploit, and it's really calculated looking at impact and probability. So if I'm trying to figure out what is my risk from this threat going against this vulnerability, I really want to think about what's the impact to me if that were to happen. Okay, I've got data coming off of an industrial machine that's telling me its temperature. What if somebody intercepts that? Who cares? Okay, I've got credit card information that's coming out of my credit card reader. What if somebody intercepts that? Different impacts. What's the probability? I'm in a closed network in a factory floor with this piece of machine talking to that piece of machine, and there's an air gap all around. What's the probability of somebody gaining physical access and getting into that system? Very small. Oh, well, I've got something that's going out and being distributed over the internet. Anybody in the world can see those packets. So what's the impact and what's the probability, and how am I going to weigh those things to really determine what the risk is? So if you look at how IoT security is attacked, a whole list of common ways that you may try to get this. You may get loss of confidentiality. You may get loss of authentication. You may get an access control attack. If I can elevate my security, my permissions, I don't need to do a lot of hacking. You let me in because you think I'm supposed to be there. So how do you defend against those? How do you predict, understand, and analyze those kind of attacks. The most academic and the most complete and thorough way of doing that is attack tree analysis. These are multi-level diagrams that you build out, and they've got a root, and they've got children and parents. They show how an asset might be attacked on one threat. And they're actually very cool to think about if you're a logical sort of programming kind of person. Here's one that's sort of an example from an industrial setting. This isn't really programming per se. But what you've got is a threat. Physically damaging cooling pumps. Okay, that might be something that somebody's trying to do as a threat to my facility. So this shape with the little curved top is an and, which means everything under here must happen for that to happen. Somebody has to gather information, they have to compromise my perimeter security, and they have to sabotage the pumps or the coolant pipes. Okay? How do they compromise perimeter security? The little pointed figure is an OR. So they can either place an authorized insider in the plant or they can force entry. Well, how do you place an authorized insider in the plant? You blackmail or intimidate somebody, or you insert a sympathizer. To do that, you've got to create the trained agent, you got to apply for employment, you got to pass the screening procedures. Same thing over here on the sabotage. So it really breaks down threats to a very granular level. And that's for one pretty simple threat. So the idea is that you create one of these for every single thing you can think of that could possibly happen to your system. And you run it all the way down to the roots of what you've got to protect against. And you can look at these in the combinations and say, in order to prevent this, if I eliminate that, it can't happen. Okay, what's the probability I can eliminate that? Okay, these are an OR, that's an OR, so I would have to eliminate that and that. Okay, how can I do those? And there's software tools that'll help you do that. They do nice graphics. They have a lot of additional tools to do that. This is sort of based on fault trees and threat trees that were developed by aerospace industry and the Department of Defense in the 50s or 60s, I think, to analyze things that you really don't want to fail, like airplanes. These, to be thorough in your security defense, you should sort of start out building these at the beginning of a project. You should maintain them throughout the project and throughout the life of the product. A massive amount of work. Again, go back and assess the risk. What's the cost of this happening? What's the likelihood that it happens? The higher that is, the higher that calculation goes, the more time and the more value this applies. So if we're making a survey system for hospitals and doctors, that's one level of threat analysis that's needed. If we're making pacemakers or automatic cars or nuclear power plants, that may be a whole other. So we've assessed the security. We can look at our problem domain and we can figure out what sort of threats they are, what sort of vulnerabilities we might have, what sort of risk that represents. We can start our threat trees and look at ways that people might come to get this. But how do we build IoT security as we're going through a project? It must be built in from the beginning. You hear that about a lot of things, but I always like Donald Knuth's quote that premature optimization is the root of all evil. That doesn't apply to security. You can't come in and layer it on afterwards. You can't say, oh, we'll take a little security now that we've got this built. There's help out there. Microsoft has developed a sort of a templated approach called the Security Development Lifecycle. Go out and look on their website. It describes this whole life cycle for applying security to IT projects. And I love it that it starts in training. Before we've even started the project, let's make sure everybody knows what they're talking about and knows what they're doing. But it goes through training requirements all the way up to release and response. What happens when this thing is out in the wild and things start happening maybe that we didn't know about and didn't predict? It's used in ways or in environments that we didn't know about.